We're looking at the kinetics and multiple choice review for the end of the year. Let's start with the first one. So all these questions are talking about 1 to 4. We have the steps of a mechanism here, and in number 1 they want to know what is the overall balanced equation for this reaction. So you remember that in order to figure this out, all you need to do is remove the intermediates, remove the catalysts, and see what's left over. So I'm going to strike out C here because C is an intermediate. Remember, intermediates get formed and then get consumed in the reaction. I'm also going to get rid of D because it is also an intermediate. And then B is a catalyst. It was there in the beginning and gets reformed at the end. So you'll notice what we're left with is a couple of A's, and the product is only going to be E. Oh, no, there's a C too. So a couple of A's plus a C goes to E. The correct answer is likely to be D. Now you'll know it's likely that I will have said in class that you can skip 2 and 3, and it's because there are some flaws in these questions, but that doesn't mean that they're not good conceptual ideas. If you want to skip directly to 4, then obviously you can fast forward a little bit. So let's look at 2. What is the function of species B? Well, we already said that species B was there in the beginning and was reformed at the end. So species B is definitely a catalyst. So that's one thing that we know. And the other thing I want to remind you of is in reactions, what keeps reactions from going fast is this energy of activation. So that's the energy of activation. And what catalysts do is they very often will lower the energy of activation. Sometimes they'll flat out change the mechanism, and you may get lower plus a little bit of a change to that energy of activation that implies it's a different mechanism. But the things we know is it's a catalyst, it lowers the energy of activation. And so let's look at our answer choices. So D is definitely correct. It does lower the overall energy of reaction. C, it is a catalyst which changes the overall order of the reaction. So that's the part that's a little controversial here, is you remember that when you write a rate law, it is possible to have a catalyst in your rate law, and it can be a variety of orders. And of course, you could have something else if you in there as well. So when they say it changes the overall order of the reaction, yeah, it very well can be, but it's hard to know whether they mean the reaction could occur without B, because some reactions can occur without the catalyst. This one would be a little bit more difficult because you can see that B is something that would end up in your rate law, and we'll see that in number 3 here in just a minute. So that's the reason we're not doing 2, is because the only answer that's flat out wrong, it might be B. Let's see, it is a reaction intermediate. Yeah, it's definitely not a reaction intermediate. But the other 3 are arguable depending on how you view it. And let's look at number 3, even though it seems to have an issue as well. So they want us to find the overall rate law of the reaction. And here's the key piece of information, knowing that step 2 is the slow step. So if this is the rate limiting step, and I actually am going to write it in more formal language, it's the rate limiting step, then it's the one that we're going to use to determine the mechanism. So remember, the elementary rate law for that reaction is rate equals K. Don't forget so remember, this is not the equilibrium constant. It's a rate constant, but we still need to put it in there. And we're not doing products over reactants here. You only include reactants. So the concentration of C, and it would be to the first order, times the concentration of A. So even though this isn't a great question, let's review a few things here. One is these orders here, remember, you can't typically determine them from by just looking at the stoichiometry. So you might wonder, well, why did I just do that? And the reason is because we're not saying that this is the rate law. We're proposing a mechanism for this, right? And this language that they're using is a little sloppy. What is the overall rate law? They're saying, what would be the proposed rate law if this was our hypothetical mechanism? So we're doing this, but remember, to determine the actual rate law, you need a rate data table, which you'll see later in the review. In any case, so you'll remember that I cannot have C in here because C is an intermediate. And so then we rewrite the rate law with the things that made C. So C was made in step 1 from A and B. So there was the stoichiometry was only 1 for each one of those. So you remember, we can't do this we can't use the stoichiometry for orders except when we're just making a proposal for a mechanism. And in the end, I might neaten it up a little bit by just pointing out that it would be second order in A and first order in B. And so that would be the answer to 3, and you can see that it's not a choice. So let's look at 4, and 4 is it's a good conceptual question. They want to know why increasing temperature causes the reaction rate to speed up. And I'd encourage you to think about collision theory, right? Collision theory is usually the answer to why do things go faster. You remember, collision theory has 2 parts. One is in order for a reaction to take place, the 2 things that are reacting need to collide with each other with enough energy to make the reaction occur. And then the other thing is they have to collide with the correct orientation. So it could be that this one has to be oriented this way to get it to collide. So energy and orientation are the 2 things that we can do to speed up a reaction. Remember, energy, we can just increase the temperature and a higher fraction of the molecules will have the energy in order to do the reaction. Orientation we could possibly have an impact on if we chose the right catalyst, if you can get a catalyst to sort of hold the molecules in the correct way. So let's look at our answer choices here. So I kind of like B. B looks pretty good. The various molecules in the reaction will move faster and collide more often. It is true that colliding more often and with more energy is a great choice. So I think B is going to be our answer here. Let's look at why the others aren't, though. A, it is endothermic reaction that needs energy from an outside source. So in endothermic reaction, you remember the reactants are lower in energy than the products. It's endothermic. You do have to add energy in to get this reaction to occur, but the amount of energy you have to add in is from the reactants to the product. This is the delta H of the reaction, and that's how much energy you have to add to get the reactants to a higher potential energy, like the products. But this thing right here, the energy it takes to go from the reactants to the transition state, is actually what determines how fast the reaction goes. Remember, the top here is the transition state, and the energy is the energy of activation. This is what determines how fast a reaction goes, not how much energy it takes to get to the products. In other words, you could have a reaction that is endothermic that has almost no energy of activation. And it's still going to take energy to get it to go, but it's going to be fast as you heat it. So this A is playing on this idea of not understanding the difference between the speed of the reaction and whether or not the reaction will occur. All right, now we get down to C, and this C is another important one. When we increase the temperature, one thing to remember is it does not change the potential energy of the reactants or the products. And I wish I hadn't made such a mess here, but the potential energy of the reactants and the products is determined based on their delta G and all those thermodynamic values. It is not being impacted by the temperature of the room around it. What temperature does, it also does not, by the way, change the energy of activation. This is how much energy it takes to sort of collide and get the reaction going. All temperature does is it increases the fraction of molecules that have the energy to do it. So to do the reaction. So if we look at a different kind of graph, which is a Boltzmann graph, and you remember Boltzmann graphs, what they're doing, they look sort of like this, and what they are is they're sort of a measure of the kinetic energy of the molecules. And let's say that the molecules have to have a certain amount of kinetic energy. And so this is like number of molecules over here, you know, as in how many of them have a certain amount of, I meant to be molecules. So, you know, not very many of them have low energy because it's at a high temperature. A lot of them have a certain energy, but it takes, let's say, this much energy up here. These molecules that have that much energy have enough to do the reaction. And what changing the temperature does is it shifts them all to a higher kinetic energy. And so what will happen is you'll get a bigger fraction of those molecules that have enough energy to collide and actually do the reaction. So C is wrong because the overall activation energy does not change. And then D, a higher fraction of the molecules will have the same kinetic energy? No, I mean, we've seen in the Boltzmann graph they have a variety of kinetic energies, so that's sort of just poor language. Yeah, so I think in the end, B will be the correct answer. Number 5, under which conditions would the order of the above reaction double? So what they're after here is, you notice they give us a reaction, and it's really important that we pay attention to the rate law. So if you're looking at the rate law, you can see right away that of the two reactants, which one is not changing its concentration, won't speed up the reaction at all. And the answer is B. You need B to do the reaction, but because B isn't in the rate law, doubling or tripling its concentration is not going to change the rate. So when they say which of these would cause the reaction to double, it's not going to be B. So we can rule out that right away. If we double the concentration of A, remember this one's first order because they don't have anything there, and that means that there's a direct relationship. If you double the concentration, you will double the rate. You remember that if the order had been second order, that would mean that if I double this concentration, it would go 4 times as fast because it's squared. If I had a third order reaction, if I double the concentration of A, it would be 2 times 2 times 2, so because it's cubed. So here I think A is going to be a great answer. C definitely not, and D, changing the concentration has no effect on the reaction order. That's not true because we know A is in the rate law.